Hello, everyone. We continue the optimization theory. This is in session 3 now. We have seen already how to find the critical points, which can be a maximum or minimum point, or inflection point using mathematical approach. We're taking the gradient, so we have some conditions. It is known as KKT conditions, which including that the gradient should be 0, and also the Hessian matrix should be positive definite in order to find that point is minimum point. And also we saw how to solve the problem in case we have constraint optimization, where we have like either quality or inequality constraints. However, unfortunately, most of real optimization problems in real world, they are very complicated in order to be solved like in that simple way. Just we take the gradient and both it is equal to 0. Many problems cannot be solved in this way, since the resultant can be very complex, so it might represent like too many solutions, and also the computation requirement to have that solution is high. And moreover, that in many situations we don't have a closed form formulation when we take the gradient and the of the cost function. In many situations that we don't have a closed form formulation for that to investigate it with the searching techniques. There is also another problem that, as it is shown in the slide here. So, in many cases, that we have online problem. It means that we have inputs, as we can see here. So we have inputs, and also the input, when it is applied to certain system or certain model, it will have some output. But this output that we would like to have some desired output, so we want to teach this model, and we want to update or adapt the parameters of this model in order to minimize the error. What is the error? The error is the difference between the output and the desired output. So we have vector of errors, and this else should go through some optimized adaptation for the weights here in order to minimize the error. So such kind of a problem is, it can be solved only like in iterative method. So we apply the first input, we adapt uh, the error, and we apply the second input, we have the output, and we subtract the output from the desired output, we have the error, and then we use this error to adapt the algorithm, and so on. So the optimization problem, that the minimizing of the error, now we are looking for the minimization, or minimizing this error, or the average of this error. So to achieve that, we need some iterative method. So iterative methods are needed like in online problems like this one, or in very complicated problems that, or complex algorithms that cannot be solved like in closed form. Okay, now how can we do that? So we will show at least two methods to do that. One of those methods are very famous, is called steep descent method. So now I will show it in a single variable, and then we will see in the multi-variable case. So in single variable, if we take this cost function, or the error function, actually in general the error function, let us call this error function as f of x. Okay, so the error function is f of x, and this f of x is always greater than or equal to 0, because it is error function. It is like mean square error, which is always positive. So we have f of x which is greater than or equal to 0, and we are looking for x which will minimize f of x. Okay, usually sometimes we write it like that, like x star equal to the argument which minimize f of x. Okay, so now assume that f of x is either unconcentrated optimization, or might be concentrated optimization, but we have already the Lagrangian multiplier inside it. So now we are looking for the x star which minimize this f of x. Okay, in general, if we say that f of x, okay, and if we like to expand this f of x, with the Taylor series expansion. Okay, and let us see how f of x plus delta x, okay, will be expanded around f of x. So the expansion will be that it will be f of x, okay, plus delta x times f dash of x plus delta x squared divided by 2 factorial f double dash of x, and so on. So this is the expansion according by using Taylor series expansion for a single variable problem. Okay, now we can approximate this Taylor expansion as this way. So if x plus delta x equal to f of x plus delta x times f dash of x plus some that this will be the error. So now we have approximation, and the error will be in order of delta x square. Okay, so now we can approximate this expansion with this like equation where we have f of x plus delta x times f dash of x. Okay, now we know that f of x is always greater than or equal to 0. Okay, and this delta x is the direction or where we should like adapt x in order to minimize f of x plus delta x. So because we like to solve this problem in iterative way, so what it means that if we are going in the right direction, then f of x plus delta x must be less than or equal to f of x. Okay, so if we achieve this one, if we achieve that the delta x, the right correction of delta x to make the new adaptation of x to be that f of x plus delta x to be less than f of x. Okay, now look to this problem. How can you guarantee that f of x plus delta x to be less than f of x? Of course, the answer is very easy, that delta x times f dash of x must be less than 0. So if it is negative, then this will be achieved. So if we say that delta x times f dash of x, okay, should be the multiplication should be negative number. So we can say that, for example, this should be less than 0. So if we make this negative number, then we guarantee that or less than or equal at least, because if we reach to the optimum point, then we will stuck there. So this will be achieved when delta x equal to delta x equal to minus f dash of x. Okay, delta x equal to minus f dash of x. Of course, here we multiply with a single parameter or with eta. This eta is called learning rate. This eta is called learning rate, and eta is greater than 0, is a real number greater than 0, and we can see later that eta must be less than 2 as well. Okay, and to guarantee, because if eta is large, then this algorithm it can diverge, and if eta, even if it is less than 2 or is less than 1, but it is large enough that it might overshoot the direction, so we can also go like beyond the minimum point, and then it can diverge again. Okay, so because remember that this is just approximation, because we have omitted all elements with delta x square. Okay, now what is delta x? Actually, delta x is the difference in movement. So we can say, I can write it here to make things clear, so it will be with different color. So we can say that x at iteration t plus 1 equal to x at iteration t, because xt plus 1 minus x at t is delta x. Okay, I do take care to just show what I am doing, equal to xt plus 1 minus xt. Xt, it means that the iteration number, okay, it is discrete. Okay, so this delta x equal to xt plus 1 minus xt, then we can take minus xt to the other side, that will be xt minus eta times f dash of x. of course, of x at iteration t. So by doing this iteration, then we can reach to the minimum point, or at least to the extreme point. But here it is descent, the steep descent algorithm, which means that it will go to the minimum point. Okay, and how it works. So let me go to the another slide. Now if we have certain like slope like this one, okay, and this is the optimum point that we are looking for, and we are here, for example, okay, so this is x, this is x at t. Okay, now where we will be at xt plus 1, so xt plus 1 will be xt, okay, and then it will be minus eta is the adaptation rate times f dash of x at t. So if you take f dash here, it will be the slope, as we said before. This will be the slope. Okay, then you can see here the slope is negative. This f dash, it will be negative, so it will direct us that in order to reach to the minimum point, we have to go to this direction. So it is negative, and here we have negative, so it will be positive. Then the next xt plus 1, next xt plus 1, it will be xt, this xt plus some value alpha, that then we will come here at xt plus 1. So actually f dash, it gives us the direction where we should go. Okay, and this eta is the adaptation rate. If the adaptation rate is too much, is too high, we might jump from this point to somewhere here or somewhere above here, and then this can reduce actually, and actually in sometimes it can even diverge the converge the iteration, so we will not reach to any point, just we go to infinity. So we should select eta carefully, as eta the adaptation rate becomes closer to zero, as becomes very small, then it is guaranteed that we will reach to the optimum point, but it can be very slow. If it is large, then we can approach faster, but we have the dangers of being diverge. Okay, so we need to compromise between these values. Of course, we can use the information in the second order, which is called the Hessian or the second derivative, in order to improve our convergence to this to the solution. Okay, and now if we look to this to this algorithm, now we start to converge step by step until we reach to this point. At this point, actually, f dash of x at this point, x star equal to 0, which means that at that point xt plus 1 will be the same as xt, and this will be achieved when t goes to infinity, or of course after enough number of iterations. It depends on the how much slope that we have in this single variable problem. So this called a steep descent algorithm. Okay, now let us expand this for multivariables. So how to expand this to multivariable? In multivariable, where we have like x equal to vector of x1 x2 up to xn, so we have vectors. The Taylor expansion in the vector space for this one is equal to that f of x, I make it a little bit bold. Remember that this should be greater than 0, greater than or equal to 0. Okay. Okay, sorry, I can just this one. Okay, so plus delta x. Okay, this will be the same, so it will be x. Okay, sorry again, this will be f of x. Okay, it as before, a plus delta x transpose. Remember that now delta x actually is a vector. It is a vector. It is a vector. Actually, it is a column, because x is a column, so delta x is a column. So delta x equal to delta x1, delta x2 up to delta xn. Okay, so it is a vector. So we take the transpose of this vector to becomes 1 times n times the gradient of x of course, f of x. So the gradient will be also a column vector, contains the differentiation of f of x with every x1, with x2, and with xn. So here we have the dimension of 1 times n, and the dimension here will be n times 1, so the result will be a scalar. Okay, plus the second order, we can at the moment we can say that the second order is in the order of, and the third, and so on. So the error here will be with dominated with delta x, times x, like some norm square. Okay, some norm of delta x square. So this will be the error here. I am coming soon to talk about the Hessian matrix here, but let us first talk about the simple steep descent. Okay, again the same concept that we saw in the single on a variable, that we need after we have this step in delta x, we need that f of x plus delta x must be less than or equal to f of x. Okay, and this will be achieved when this element is less than 0, when this element is negative. This element is negative, means that delta x equal to the adaptation rate, or the rate or the learning rate eta, times, of course here, minus delta x of f of x. So this is called the steepest descent algorithm in multidimensional case. So delta x actually is equal to x t at t plus 1 minus x at t, and this equal to minus eta delta x of f of x. Okay, and it means that x at iteration t plus 1 equal to x at iteration t minus eta delta, the gradient of f of x at iteration t. So this is the steepest descent algorithm. Remember that again, that eta should be small enough. For large eta, we might have the problem of divergence, or the problem of overshooting the minimum point. Okay, so but by this method we can solve many algorithms with the steepest descent, and we approach to the optimum solution with that one. Okay, now what happened if we look to the third item in the gradient algorithm? So in that case, we can say that f of x plus delta x equal to f of x, okay, and plus delta x transpose times the gradient x of f of x, okay, plus half of delta x transpose times the Hessian H matrix times delta x, and then plus the other or higher order elements, which will be dominated by delta x with some norm for the cube dimension, or the power of cube. So now we have more accurate representation about the expansion of the cost function, or of the error function, around delta x by including the Hessian matrix. Including the Hessian matrix, actually, it can also guarantee how to approach the solution. Actually, if H is a positive definite matrix, which means that all lambda from lambda 1 up to lambda n are positive greater than 0, then this guarantee that we can the point that we will converge to will be like a minimum point, will be the minimum. Okay, again, if it is all of them, they are less than 0, then it will be maximum point, and if we have like mixing of them, or we have zeros here, then we might have saddle point, or or inflection point. There's one thing more important here. Actually, we can guarantee and we can show that the convergence rate here depends on the distribution of the eigen values of the matrix H. Actually, it depends on the condition number of matrix H. Remember that the condition number of the Hessian matrix H is the maximum of lambda I divided by lambda j, or in other words, it is maximum lambda divided by minimum lambda, because it is symmetric. So all of them, they will be linear, so they will be real numbers, so we don't need to have the absolute value. We don't have complex eigenvalues when we have symmetric matrix H. Okay, so this is the condition number. So when we have both condition number, actually the adaptation rate will be very slow. When we have good condition number, small condition number, then the adaptation rate can be very fast. Actually, the distribution of the eigenvalues could be used in order to specify what is the optimum learning rate sigma. Maybe there is no need to go more details here about the investigation and the analysis. However, that it is not difficult, by the way, because you can do that based on the iteration method. So when we have iterative method, then we will have adaptation with H, and it will be like H squared, H cube, H of 3, and so on. Then we make singular value decomposition, or we can make eigen decomposition of matrix H, and then we can see the impact of the diagonal elements, which will be lambdas in this way, on the convergence rate of this algorithm. This could be done in different video, but now what I want you to know, that the concept of a steepest descent is based on that criteria, that xt at time t plus 1 equal to x at time t, okay, and it will be minus the adaptation rate sigma multiplied by the gradient x of the function f of x. So it is actually very easy to solve. It is you can put it as like in a loop of in MATLAB or any programming package, so you can solve this one. And let me take a simple example here. So assume that we have this f of x that we have, and it is like two parameters, like we have x1 squared plus x2 squared minus x1 times x2, okay, minus x1 times x2. Just an example, okay, and maybe plus some number like 5, for example. And now let us how to build the iterative method based on this. In this case, for example, you can say that as we said, x t plus 1 equal to xt minus eta times the gradient x of f of x at time t, or at the iteration t. Okay, this one is simply x1 at t plus 1, and this will be x2 at t plus 1 equal to x1 at t, x2 at t, okay, minus eta is just like linear algorithm. It can be, of course, adaptive, or it can be fixed. And here we have the gradient of fx with respect with x1 and with x2. It means that we have vector in the beginning that we differentiate with respect with x1. It will be 2 x1 at t, okay, plus, of course, here will be 0 because we differentiate with respect to x1, so it will be 0. And here we will have minus, actually, it will be minus x2. It will be minus x2. Okay, it can be, of course, at time t. And the second equation, it will be x2 at t plus 1 equal to x2 at t minus eta times, and now we differentiate this equation with respect with x2, so we will have 2 x2 at time t, okay, and then minus x1 Of course, you can use the latest adapted value t plus 1, but sometimes it can make a problem in the stability. So to be more sure, that you can just put here at time t. Okay, let us start. For example, if we start with, let's say, x1 0 equal to 1 and x2 0 equal to 1 as well. How this will be done? So x1 at time 1 equal to x1 at time 0, because this is t plus 1 and this is t. At time 0 is 1, so it will be 1 minus, let us take that eta equal to 0.5, for example. It becomes minus 0.5 times 2 times 1 is 2 minus 1. Okay, so x1 at 1 equal to 1 minus 2 minus 1 is 1. 1 times 0.5 is equal to 0.5. So 1 minus 0.5, it will be 0.5. And x2 at iteration 1 will be x2 at 0 is also 1 minus 0.5 times 2. X2 is 2 minus x1t. It will be also minus 1. So it will be the same as 0.5. Okay, now we substitute in the next one. So x1 at 2 equal to x1 at 1 minus eta times x1 at 1 minus, sorry, 2x1 at 1 minus x2 at 1. Yeah, so now this will be x1 at 1 is as we saw, it is 0.5 minus 0.5 times 2 times 0.5 is 1 minus x2 is 1 of 1 is 0.5 minus 0.5. So 1 minus 0.5 is 0.5. 0.5 times 0.5 is 0.25. 0.5 minus 0.25 is equal to 0.25. And I may guess that also x2 at iteration 2 will be also 0.25, because they are similar. Okay, now we go again and make the adaptation, and then we can continue in this way until we reach that x1 at time t plus 1 equal to almost x1 at time t. Then it means that actually we can put I here. So for all I equal to 1 and 2, so in that case we come to the stability solution or stable solution, and we have converged to the optimum solution. Is it optimum? It will be critical and it will be minimum point, but no one can guarantee or can say is it like local minimum or global minimum. Okay, how to say that is it local or global? Of course, for some cases like this simple case, we can say that the minimum will be global, because it is convex. So wherever you can guarantee that or you can prove that the cost function or the error function is convex, then the minimum point that you will reach will be the global minimum. Okay, however, if you cannot prove that it is convex, then you cannot say that is it a global minimum or just a local minimum. And if you don't know if this local minimum is the best, which means that it is global, or we have much better solutions that somewhere. So because this method, this is the one of the main disadvantage of steep descent algorithm, that it will stuck in the first local minimum. So let me explain this with this. It is not easy to draw a three-dimensional figure, but I will do my best to do that. So now assume that we have such okay, so it is like this figure. Okay, so now you can see this is a surface. Okay, we have some critical point here, but of course it seems that it is maximum. So and the steep descent algorithm, always it will go to the minimum point. It will not, it shouldn't go up. Actually, it should always go down. Okay, it depends on the slope. And now assume that somewhere in this direction we have like uh, we have some like this point minimum, another minimum point, or we have minimum points here. And now when we are going the steep descent algorithm in this two-dimensional cost function. So this is f of x, and we have, for example, x1 and x2. So now assume that we are here, somewhere here, base it on the gradient, and we can go down, and every time we can go down, we can go down, of course, with a smaller speed, because as you are approaching the minimum, the slope becomes like this, and since the slope becomes less, then the adaptation factor will be smaller and smaller and smaller, and then we can reach very slowly until we reach to the minimum point. So now we reach to this point. Actually, this point, like it is like some local minimum. Of course, if you go further, you can, there is another minimum here. Okay, but our algorithm actually will stuck here, and will stop here. Okay, of course, we have some techniques that we can push this outside by adding some noise, for example, strong noise, but this noise should dimension, or should reduce with time. It is called annealing methods. So we can add some noise which can be reduced with time, so to get out from local minimum. Or we can also push this with large eta if you are not interested in this minimum, and hopefully that we can find some other minimum somewhere in this two-dimensional problem. Even in this two-dimensional problem, things are not so straightforward. So think, if you have 100 dimensions, so it is absolutely very complicated to search. Because, for example, if I am here, should I go to this direction, or this direction, or up, or in that direction, or in that direction? So I don't know actually where there will be like better solution than this point. This is only in two dimension. But what if we have like 100 space, 100 dimensional space? It becomes much more complicated actually to search where we should go. Okay, so we always need some more sophisticated algorithm. However, this steep descent algorithm is the major optimization techniques used, at least in the conventional or in the traditional neural networks, and many other actually algorithms, they use this steepest descent algorithm. So we try to reach to this minimum point by going step by step toward, like, depends on the slope at each point, until we reach to the minimum point. So now we understood, at least roughly, what is the meaning of steep descent, how we can solve this optimization problems in uh, iterative way, iterative methods, which is widely applied in neural networks, in deep learning. Many algorithms we use this approach. Okay, that's it for this video, and see you in the next one. Thank you for your time.